Okay, dear students, let us see what is there in this question now. On a guitar, the strings played vibrate between two fixed points. The frequency of the vibration is modified by changing the string length using a finger. The different strings have different wave speeds, and that is due to the different cross section area of the strings. When a string is plugged, a standing wave forms between the bridge and the finger. So it means like they're talking about this bridge, and here is the finger, and the total length of the string between these 2 points is 62 centimeters. Fine. And moving next now, reading the question. The string is displaced by zero point 0.4 centimeters at the point P to sound the guitar. The point P on the string vibrates with simple harmonic motion in its first harmonic with the frequency of 195 Hz. The sounding length of the string is 62 centimeters. So the length of the string is 62 centimeter. Outline how a standing wave is produced on a string. So first of all, like this question is for 2 points, point number A. So this question is completely theoretical and outline how a standing wave is produced. So we would be reading what is given in the mark scheme, but overall what we have to write, we have to say that standing waves are formed when two waves are actually superposing each other. The two waves which have the same frequency, they have the same wavelength, and but they are traveling in the opposite direction. So when those kind of two waves they superpose each other, they give rise to a standing wave. That's it, nothing more than that. And we can see the mark scheme, and I will read you the answer here. Yes. So the answer here is the traveling waves move along the length on the string and they get reflex. Superposition of the incident and the reflected wave. The superposition of the reflection is reinforced only in the for certain wavelengths and all that. So this kind of description can be given for this question. Fine. Let us now go to B1. Show that the speed of the wave on a string is about 240 meter per second. So basically we want to find the velocity v, the speed of the wave. And I think we have only one such formula which talks about the speed of wave, and that one formula is v is equal to f lambda, where lambda is the wavelength, f is the frequency. So definitely we have to find these things. Frequency is already given, by the way, 195, but the wavelength is not given. If we are able to find the wavelength of the wave which is moving in the string, we can very well find the velocity of the wave. How are we going to do this now? Okay, so what is the other information that we might be losing on? Yeah, see, here is the information. It says that in the string, first harmonic standing wave is created. So first harmonic standing wave means like if this is the string and these are the two fixed ends, so the standing wave will be created somewhat like this. Somewhat like this. So this is the standing wave that is created here. So this is plugged at the center point, which is point P. So this is definitely the amplitude, and the amplitude is also, by the way, given in the question, but we are not considering that as of now. So this is the amplitude. So now you see this thing. What is this? Like, isn't it the half of the wavelength? You see, it is the half of the wavelength. The length of the string is L, but the wavelength is half. So lambda by 2 is equal to L in this particular case. Like if I go for second harmonic, let us say, this is the string. So second harmonic will look somewhat like this. Like this. So this will be the second harmonic. Yeah, and clearly this length of the string is equal to one wavelength. So this is the second harmonic, and in this we can always say that wavelength is equal to L. But this is our case in this question, so this is just for the introduction or understanding. Here I can say that L will be equal to lambda by 2. Accordingly, we can find the wavelength because length is given as 62 centimeters, and so wavelength will be equal to 2L, which is given by 62 multiplied by 2. So that will be 124 centimeters. So this is the wavelength, and please keep units in your mind because these are not SI units. We have to convert it into meter if we are going to find anything with this. So 124 centimeter is the wavelength, and I told you that the velocity is equal to lambda into F. Wavelength is found to be 124 centimeter. We divided by 100 because we want it in meters. Frequency is given as 195. A very simple calculation will be involved here. So I'm using my calculator now. 124, 195 divided by 100. It is 241.8 meter per second. And what is this? This is the velocity of the wave. We are not talking about the velocity of the particles of the string. Like we're not talking about the particle P or particle Q, particle R, S, T. We're not talking about them. We are talking about the disturbance that is traveling from, let us say, this end. The first end is like P, the second end is Q. So the disturbance is traveling from P to Q, let us say. This is what we are saying. Anyways, I'm just erasing this P and Q because there is already a P there, so do not get confused. Yes, the answer is 241.8. This is how we do it, and let us see what is the answer in the mark scheme. Are they having the same answer? Yes. So instead of 241.8, they have given 242 meter per second. Clearly, they have also found the wavelength, and they have done the same thing that I have told you to do. So this was B1, and let us go to B2 now. So B2 question is sketch a graph to show how the acceleration of the point P varies with the displacement from the rest position. Okay, so you want to draw the graph between the acceleration and the displacement, and he's actually talking about the point P. In regards to point P, he has already given in the statement above that point P is actually under simple harmonic motion. So it's clearly given there. So there is no question. Definitely, this graph is pertaining to simple harmonic motion. Simple. So we know that the acceleration in the simple harmonic motion is actually minus omega square x. Clearly, x raised to power 1. So I can say that the graph between a and x will be a straight line, and that even with the negative slope. So you can see this is negative omega square, where omega square is a constant. So it means that the slope is this. I am comparing this thing with y is equal to mx plus c. The students, those who are maths AHL, or they know what is this equation, so they are now able to understand better. So I can say that this is going to be a straight line with a negative slope. So we can just draw the line like this. That's it. By the way, the same question is given in the book Sokos. If you have the Sokos PDF or something, you can open the book and you can see this graph is given in that book. And I think it is the first example in 4.1. So you can refer to that to understand it, like if you are having some problem here. Anyways, so this graph is done B2, and let us see the mark scheme again. So yeah, they are not given this. So the straight line through the origin with the negative gradient, clearly. Let us now move to B3 and see what are they asking. Calculate in meter per second the maximum velocity of the vibration of the point P when it is vibrating with the frequency of 195 hertz. My dear students, now he's actually talking about the maximum velocity of the particle P. Earlier, he was talking about the speed of wave, which was coming out to be 240. So it is always handy if you write it like this. VW is the speed of wave. Here we are talking about VP, like V particle. So I generally write it like this. VW is like speed of wave and VP is the particle. So now he's talking about the maximum velocity of the particle, and it is undergoing the simple harmonic motion. So we already know the formula, and the formula is also given in the data booklet. So you can see from that also. So the velocity of the particle, and that even maximum, that is why I've written 0 here. It means like I'm talking about the amplitude that is given by omega naught, sorry, x naught omega. X naught is the displacement of the particle, which is earlier, I think, given there. We will see what is the X naught. And omega, we will find it from 195 hertz. So, yeah, here, do you see this? I've just moved the screen. This 0.4 centimeter is the displacement. Like this is displacement. So, that displacement is the maximum displacement. So, this is the amplitude. So, clearly, the amplitude is 0.4 centimeters. So, now we have to see what we can do about that. Okay, so 0.4 centimeters, and omega will be 2 pi f, 2 pi into 195. Yeah, So there we go. This will be the velocity of the particle, and you can find it. So I'm not calculating this now because it would be consuming a lot of time. I will just show you the mark scheme, and they would be doing the same thing. You can use the calculator and see if you're getting the correct answer. Okay, so this is B3 that we're talking about. Yes. Yeah. So the maximum velocity occurs at x is equal to 0, he says. Anyways, so this is uh, 2 pi f square root of, yeah, why is he using square root as well as he's squaring it? Do you see this? Like, this is really weird. So he should be writing as 2 pi f into x naught. So x naught I have written as 0.4 divided by 100, which is literally 0.004. Now he's squaring it, and also he's taking the square root there. So that is not required to be writing. So I believe like we would be getting the same answer because they have done exactly the same thing that I had done. No doubt about that. So this is how we do it. Now we are moving to B4. This is B3. Okay. Calculate in terms of g the maximum acceleration of the particle p. Now, one thing is clear that the particle b is undergoing simple harmonic motion. So if we are using v naught is equal to x naught omega, why can't we use a naught is equal to x naught omega square? Because even this formula is given in the data booklet there. Like, this is for the maximum acceleration in the case of simple harmonic motion. So it is x naught omega square. This is a naught. Now, so we are going to apply this formula if we want to find the magnitude. So let us do it. A naught is equal to the displacement, which was given as the amplitude, 0.4 centimeters. So it is converted into meter. Omega, I don't know what omega is. So we are going to again write it like this. Omega is like 2 pi f. So this is 2 pi f square. And okay, just for the sake of people, those who are not able to understand this, yeah, omega is equal to 2 pi f. So this, and now you are going to substitute your value. So let me see if I can solve this and see what is the value that we are getting. 0.4. Yeah, I'm getting an answer, and 0.4 centimeter. Now this is converted into meters, no doubt about that. 4 pi square 195. Where is there any error there? 195, because I am getting 6,000 something, 6,000 meter per second square. But I think this is too much, but might be like this is giving us this answer. Possibility that this will be the correct answer. We will see. So now let us concentrate on the question back here again. So whatever is the value coming from here, I'm sure that this formula is correct. So definitely the answer should also be correct. So now he says that you want to find the acceleration in the terms of g. Now, this is a really weird thing. Like, from where the gravity came in this expression, we're talking about the standing waves. Gravity has no role to play there. We are indeed getting a very specific answer, like 6,000 meter per second square. Why do you want to do that? So, for the weird question, we are going to do a weird step. And what is that weird step? 6,000, and we are multiplying it with g, and we are dividing it by g. So I'm taking g gravity as 10. So in the denominator, we are using the value of the gravity. So thereby we are cancelling this thing. So accordingly, your answer will be 600 g meter per second square. So we can say that yes, this is the value of the acceleration in terms of acceleration due to gravity. That is the only thing that I can think of. So the answer for this will be 600 g, and let us see our if they are having the same answer. Well, absolutely correct. You can see it is 600 into g. So the answer is correct. So this is the step how we do it. Okay, let us go for fifth question now. Estimate the displacement needed to double the energy of the string. Okay, so we now he's talking about the energy and what should be the displacement. It means like what should be the actual amplitude, like we are plucking the string, And he says that the amplitude for plucking the string is zero point 0.4 centimeters. So what should be our new amplitude so that the energy becomes double? So what is the formula for the energy? I'm just going to use a very simple formula, which is half kx square, which can be used for any simple harmonic motion. You see, try to understand, this is only and only for spring mass system. It cannot be applied on strings or something else technically, but every simple harmonic motion, even if you're talking about the strings, or you're talking about a body which is floating in water, or you're talking about pendulum, or you're talking about any damn thing, alternating current, something, if it is using a simple harmonic equation, that system can be compared with the spring mass system. So this formula is always valid, always valid. So whenever it comes to energy for simple harmonic motion, this is one of the very very handy formulas. Keep it handy with you. Okay, so half kx square, clearly it only depends upon the displacement that you are giving. So earlier the displacement was zero point 0.4, but now what is the displacement, we don't know. So what was the earlier energy? Half k 0.4 divided by 100 square, and you want to have double the energy, so half k a dash square. So this is the final energy, which is double of the initial energy. From here we are going to find a dash. Half and k, they're just getting cancelled out, so it will be zero point 0.4. I can just keep it in centimeters because even this will be in hundreds, so I can remove this 100. Okay, now I would be getting the answer in centimeters, not in meters. These are ratios. That is why we can do this. So 2 into zero point 0.4 centimeter square is equal to a dash square. We can take the square root. Clearly, a dash will be zero point 0.4 into square root of 2. So whatever is this value, this will be our correct answer. So if this is the new displacement, the energy is going to be doubled. Okay, so let us see the answer. Our answer is zero point 0.4 root 2 for B5, I think. Yes, exactly, zero point 0.4 square root of 2. So this is how we do that question. Now let us go for the point C. So C is the string is made to vibrate in third harmonic. Earlier it was first harmonic, now it is third harmonic. State the distance between the consecutive nodes. Okay, so how are we going to do this question? Okay, let me show you this thing. Like in the first harmonic, the it moves like this. So we just say that lambda by 2 is equal to L. In the second harmonic, it becomes like this. So we say that now the complete wavelength is equal to L. In the third harmonic, it will be like this. So this is lambda by 2. So 3 times lambda by 2 is equal to the total length of the string. And from there we can find the wavelength and all that. But here we are supposed to find the distance between the consecutive nodes. It means that just looking forward to this distance. So clearly this distance is 1/3 of the total length. So total length of the string was 62 centimeter. We have to divide it by 3. So 3 to the 6. And it will be like, okay, there is a problem. It will be 60, approximately equal to 21. You can say 20 point something. It will be 20.9. So fairly you can say it is 21 centimeters. Anyways, let us see what is the answer given by them. Yeah, even they are taking it to be 21 centimeters and approximate answers. Okay, dear students, so I think this was the last question for this paper 2 question. Yes. And so this is how we do this question. And this is Professor Varun. Thanks for joining. I believe it should be of a great help to you. Thanks for joining the YouTube channel. Please spread the channel. Please spread the name. Please tell your friends to join the YouTube channel. All the best. Bye.